Hello and welcome back to the Sports Biomechanics lecture series. As always, supported by the International Society of Biomechanics in Sports and kindly sponsored by Vicon. I'm Stuart McErlain-Naylor from the University of Suffolk, but much more importantly, I'm joined today by Kristof Kipp, who is an associate professor at Marquette University in the USA. And I know Kristof's had some really cool studies recently that I know I've enjoyed reading on the topic of weightlifting biomechanics. And for anyone who's had a look through his Twitter feed, there's a lot of kind of really cool graphics and data visualization around weightlifting that sort of are really thought-provoking for me. So I was really keen to hear some more thoughts and really happy that Kristof agreed to come and share some thoughts with us today. But yeah, I'm aware weightlifting biomechanics is a very broad title or broad topic. So I'll hand over to Kristof and then he can tell us a little bit more. Thank you.
Alrighty, thank you, Stu. Thanks for the introduction, and thanks for everybody for joining us, or for those people who might be watching a little bit later on. As Stu said, I'll be talking about weightlifting biomechanics today, and I gave it the title "Selected Thoughts" because I've taught an entire class on this topic before, and so I've just curated a couple of things that I thought might be interesting for people to listen to. And my other disclaimer that I typically give, if you pick up a little bit of an accent, I was born and raised in Germany, so German is my first language, and I actually learned how to speak English in Canada after my family immigrated to British Columbia in the mid-90s. So if I sound a little funny, it's because it's a mixture of those two, and sometimes when I get excited, I tend to ramble on a little bit. Especially if I've had a couple of beers, which probably isn't the case right now because it's 10 a.m. Although, as Stu kind of talked to me about earlier, it's pretty much 5 o'clock everywhere these days. So, okay, so today we'll talk a little bit about the sport of weightlifting, and I have a couple of slides here and videos just to kind of make a distinction that we're talking about weightlifting as in the snatch and the clean and jerk, primarily again, in relation to sports biomechanics and not necessarily related to strength and conditioning or resistance training exercises such as everybody else's favorite bench press and bicep curls. So here are a couple of videos just to kind of introduce these exercises. Here first we have the clean, or slow motion video of a lifter lifting the barbell from the floor, big triple extension, explosive extension onto the shoulders, and then standing up. There's a second part to this lift that's called the jerk that I won't be focusing much on today. And then we also have the snatch, where the lifter moves the barbell from the platform to the overhead position in one motion. So, and Naeem Suleimanul is very happy here. Probably one of the greatest sports achievements of all time, in my opinion. The only time that anybody snatched 2.5 times their body weight. So I would be pretty happy as well. Okay, so from a performance perspective, or from a perspective of studying weightlifting biomechanics, it's pretty nice because we have clear performance criteria. So we can we have a direct measurement of how much the person is lifting during the exercise. So we can quantify that with the bar mass. And then also the technique is pretty interesting, that it's not just, load up the bar with heavy weights, stand up with it, and dip underneath of it. And there are actually some very interesting biomechanical aspects that kind of manifest in this very stereotypical technique that we observe. So with respect to the weightlifting research that we do and that most people have focused on from the biomechanical side, there's some focus on the biomechanics. So we're tracking kind of the movement of the barbell through space, ground reaction forces, the forces that are interacting between the lifter and the ground, or the lifter and barbell system in the ground. And then also joint mechanics. So we're either looking at the kinematics of different body angles, body segments, and the kinetics. And then just to share with you some of the research projects that we've focused on, or kind of focus on either competition analysis or doing some work with submaximal loads in an effort to kind of look at different warm-up techniques for weightlifting. Here we have a picture of kind of our original biomechanics lab setup, where I still can't believe that my original undergraduate supervisor let us construct this weightlifting platform in the lab around these force plates with very expensive cameras, right, all around. Weightlifter not very happy as Mike Conroy, our weightlifting coach, is looking on and saying, do it again, harder, faster. So with respect to some of the variables that we actually look at in weightlifting biomechanics, the first one is bar path. So here I have kind of the stick figure drawn in to kind of show you the direction that the lifter is facing in order to provide a little bit more information or context for how the bar moves. So here we have a bar path with an initial rearward displacement during kind of the initial pull phase, followed by a secondary forward movement that is around this, what we call the vertical reference line. And this initial backward forward movement that crosses the reference line is typically what we refer to as an A-type trajectory. If the lifter exhibits a barbell trajectory, produces a barbell trajectory that doesn't follow or that doesn't cross the vertical reference line, we typically call this a B-type trajectory. And then there are also C-type trajectories where instead of an initial rearward displacement, we have an initial forward displacement, this kind of back and forth lift, and this will be classified as C-type trajectory. And typically what coaches seem to think, and what research seems to indicate, that type A and B are considered okay type trajectories if we observe these. Type C trajectories are somewhat considered inefficient, as you can imagine. Too much back and forth movement may not be good. And I'll come back to that in a little bit. So you can also then move on to some, right, from the barbell trajectory, you can calculate the acceleration and the velocity profiles of the barbell. And so I have this illustrated here. The blue line, right, from liftoff, kind of increases pretty steadily and then drops to 0 as the barbell reaches its maximum peak. And we also, if we at the same time calculate the acceleration, plot the acceleration, we have a pretty steady acceleration profile that only really drops negative once the barbell has obtained its maximum velocity and as the lifter is preparing to catch the barbell. I've just included another figure here where the trajectory is slightly different. I just wanted to show this to illustrate that there are some inter-individual differences. So what's interesting to notice here, right, is that instead of a steady increase in velocity to the overall peak, the global peak, we have an initial increase followed by a slight decrease in velocity. And so this is associated with a negative acceleration phase, right? And so there might be some applications or implications for whether this denotes a braking phase and how efficient this is. Kind of something that Stu alluded to is we've been playing around a little bit of how to communicate some of this data a little bit better, especially taking barbell velocity profile or acceleration profiles and providing that back in a format, or relating that back to a format of bar path. And I tweeted some of these pictures a while ago, and I realized that it probably would be good to also show some of these velocity and acceleration profiles so people have a little bit more of an idea of what these what these line graphs look like. With respect to the ground reaction forces, we've measured ground reaction forces during weightlifting exercises. And of course, if we're just measuring the ground reaction forces, we're looking at the force that acts on the barbell lifter system as a unit, right? So the ground reaction force that's applied to the lifter here It's obviously related to two parts. Right? We have acceleration of the barbell, as well as acceleration of the center, the lifter's center of mass. And if we kind of look at the time series data of what this looks like, we observe that there's typically this biphasic profile where we have this initial peak where the lifter is producing a ground reaction force that exceeds the system weight. A little bit of a decrease and followed by a second and larger peak. And initially this has been kind of discussed by Inoka as far back as the 70s, that we do observe this biphasic profile. And in some cases, we can even see a decrease below the system weight, or that the ground reaction force falls below that system weight. And so the terminology that we use to kind of denote these phases of weightlifting movements, right here we have the first phase is called the weighing phase, the unweighing phase, and then the weighing two phase. And so as Inoka showed in that same paper, is that we actually have, or that ground reaction force follows the barbell profile in a pretty similar manner. And so again, it seems that the ground reaction force gives us a pretty good picture of what is going on overall with the system as well as the barbell. So if we dive in a little bit deeper, look at a little bit more detail of what's going on at the level of the joints. Here we have hip angle plotted against time of what I call percentage of lift. And really, it's not the entire lift that we're looking at here. We're looking really more at what we refer to as the pull phase. We focus primarily on this phase because after this, we don't really capture ground reaction forces anymore. And so we lose the ability to apply our favorite hammer in biomechanics, which is inverse dynamics. But if we look at the kinematics of the joints during this, we still see some very interesting patterns. Maybe not so much for the hip angle, but if we look at the hip angle, we start in a flex position here, right? We pretty much extend until about 60% of the pull phase, maybe a slight dip for some of the lifters, and then we go into a final extension phase. The dark gray line kind of shows the ensemble average of, this is either 5 or 6 lifters, and then the thin gray lines kind of shows the individual variations of the lifters. So at the hip, we kind of see this primarily extension movement. Whereas if we look at the knee angle, things become a little bit more interesting, so to speak. Where if we look at the knee angle, we can start off in an initially flexed position here during the starting position. We then move towards extension. That initial extension phase is followed by a really marked rebending, reflexing of the knee, that is then followed again by an extension. So we have this extension, flexion, extension pattern that we observe at the knee. We'll come back and talk about this in much more detail later. And then at the ankle angle, we see, again, this extension, flexion, extension pattern. Not quite as marked as at the knee joint, but we definitely see this triphasic pattern as well. And so another way that we often look at movement phases during the weightlifting pull, right, or during this main pulling phase, is that we denote the first extension phase as quote unquote the first pull. The rebending of the knee joint, reflexing, we call the transition phase, or sometimes also the quote unquote second knee bend, which is then followed by the second pull, that final extension of the knee joint. Another way to look at this from maybe a little bit more complex coordination perspective, if we look at ankle angle diagrams, where we have trunk angle on the horizontal, knee angle on the vertical, The lift starts down here. Again, if we look at the coordination between these two joints, right, we see that the initial phase is characterized by an initial extension phase at the knee, where we don't observe much change in the trunk angle. So there isn't a large excursion on the horizontal x-axis. Once the barbell reaches just about the point of the knee, right about the patella, we see that rebending of the knee and followed by the final extension phase. So if we then shift gears and look at the joint mechanics, and kind of focus on the kinetic side a little bit. Here we have the hip joint torque or the hip net joint moment across the pull phase, right? So either if we say the entire pull phase or the first pull transition and second pull phase. And if I had to characterize this, right, and to say what do we see, what do we observe? We observe pretty much a steady hip extension moment throughout most of the motion, that then progressively goes to zero towards the end when the lifter loses contact with the barbell and drops underneath the bar to catch the bar either at the shoulders for the clean or overhead in the snatch. If we look at the net joint moment at the hip, and we notice that the patterning of the joint moments is a little bit more interesting than what we observe at the hip, where we have we start off with an initial extension moment, but we also see that towards the middle of the exercise, towards the middle of the movement, we actually observe a knee flexion moment that is then followed again by a knee extension moment. So it seems to match to some extent what we see at the knee joint in terms of the kinematics, where we observe that extension, flexion, extension pattern. The interesting thing here is that if we're looking at net joint moments, right, we can also talk about the implications of involvement of the extensor as well as the flexor muscles. And then if we look at the ankle joint moment profile, again, it seems to have this back and forth extension, maybe coming to almost a flexion moment and then an extension pattern again. So similar to the knee joint, but just not as marked of a variation from one to the other. So that's for the plantar flexor muscles. So where things get interesting in terms of looking at movement phases, movement control, or really putting things together from a biomechanical perspective is if we consider the kinematics and kinetics together. So here what I've graphed is knee joint angular velocity. So we have, again, wherever this dark line is positive, the knee joint is extending, right? The magnitude just gives us the velocity with which it's extending. Here, if we have a negative knee joint velocity, the joint is flexing. Magnitude gives us how fast the joint is flexing. And then we have that extension during the second pull. And I forgot I had this color coded. So we have our little extension phase here, knee joint flexion followed by the final extension phase. I'm going to try to match this up now with what is going on at the joint moment level. So I've graphed the knee joint moment down here, an extension being positive in this sense. I've flipped this from convention in order to show this a little bit better. But if we, again, take any positive net joint moment to be an extensor moment, that would tell us that the knee extensor muscles are producing an extension moment that's a net extensor moment. And flexion moment will tell us that the knee flexors are creating a net flexion moment. And then again, we have that extensor moment towards the end. And so again, we have three phases, but it's kind of interesting that if we multiply these things together, knee joint angular velocity, knee joint moment, we look at knee joint power, we come up with a curve that doesn't look like any of these. And the phases here, if I try to line up the blue and yellow boxes, right, things actually look kind of complicated. And I think this is where I start losing a lot of my undergrad biomechanics students. So I try to talk through this very slowly and deliberately. But let's analyze this step by step, right? So again, positive joint power would say that we're producing or generating power. We're doing positive work at that joint. Negative power, right, we're absorbing power during these phases. And I've labeled on top here what is going on with the kinematics. So I have, again, an extension motion that matches up with the phases that I have for my angular velocity, knee flexion motion, and then again, the extension motion. And down here, I've kind of added the labels of what is going on with the kinetics, with the net joint moments at the time. So if we walk through this, right, we have these light blue phases where, right, light blue, light yellow, light blue, which seem to match the extension, flexion phases over here, but then I have these weird in between shaded areas. And so if I start with initial extension motion, right, we see I have an extension motion, I have an extension net joint moment, right, so my knee joint extensors are generating power until I get to this part where you can see that I'm still extending, but now I have this flexion moment. So it's actually the knee flexors that are slowing down the extension and are therefore creating this absorption of power at the joint. So we'd say this is, right, characteristic of an eccentric muscle action or an eccentric action at the joint. The net joint moment continues, right, continues to exist for a little while longer, and it actually then it stays present during the movement until the joint, or as long as the joint, brings the joint into flexion. Right, so this is again what I have up here. So the joint starts to flex under the flexion moment. So here I come back to now the joint is flexing under a flexion moment. So it's my knee joint flexors that are actually generating positive power, right? So they're creating that flexion, that rebending of the knee joints that we see going during that transition phase from first pull to the transition phase. And then if we go into the second pull, right, the knee extensor moment starts, or we start producing a knee extensor moment before the knee actually is extending. So while the knee is still flexing, I have a knee extensor moment. So I have a little bit of energy that is absorbed at the knee joint again, indicative of an eccentric action at the joint that then precedes the final extension phase. And this is often, right, what we talk about when we mention the double knee bend, or the stretch shortening cycle action at the knee during weightlifting exercises, right? It's where as the knee is flexing during that double knee bend, I have knee joint flexion. But as I'm flexing, I'm actually creating this knee joint extension moment. So we can also look at hip joint powers and ankle joint powers. We can calculate those for the other joints. And so something that's kind of interesting from a control perspective, right? If you stayed with me as I tried to explain what is going on at the knee joint, it seems fairly complicated, but things get easier at the hip joint and at the ankle joint because I don't have these oscillations between positive power and negative power, positive power, negative power. So where I have 5 cycles back and forth for the knee joint, I only have 4 for the hip and 3 for the ankle. And so again, it lets us talk about the movement phases during the pull in a slightly different way than what's traditionally been used, right? So originally, when people used primarily force plates and kinematic analyses, such as in one of these classic articles by Hakkinen in 1984. We're looking at ground reaction forces throughout a clean. We're looking at knee joint angle, and we're trying to look at, we're trying to make inferences about muscle action, such as concentric, eccentric, concentric movements based on the kinematics and what we observe overall the ground reaction forces. If we then look at, if we take some of this data from what we get from the joint kinetics, we can again get a little bit more detailed information where the solid black line here are my ground reaction forces. The dotted line are the net joint powers. This is for the knee joint, hip joint, and ankle joint over here. But what I just want to point out here is that, again, as I have that unweighing in the ground reaction force, that is where I temporally observe my peak knee flexion power. That seems to coincide with that unweighing phase. Okay, so that's kind of a brief overview of some of the mechanics of weightlifting. I want to try to talk a little bit about some more research, and some, again, more thoughts that I have on where we could maybe have research go in the future. So if we look at bar mechanics, right, oftentimes we talk about efficiency, how efficient is a lifter? And the classic definition for weightlifting efficiency came from Garhammer back in the 80s. It was just a ratio of vertical work to total work that's done on the barbell. So we're just looking at overall what is being done with the barbell. And if we look at some data that he presented in one of his seminal papers in '93, we see that these efficiency ratios for different lifts definitely run the gamut, right, from 90% all the way to 100% for different lifters, different exercises, different loads. However, something that always bugged me a little bit with this classification or with this definition is that, right, the way to get perfect efficiency is that we would just, right, eliminate all horizontal barbell motion. And I just don't know how likely that is. If you talk to coaches, for example, or if we look at what we see in the literature, right? Here's data from the 1985 World Championships that was presented by Bauman in Journal of Applied Biomechanics. If we look at weightlifting barbell trajectories across a lot of different weight classes, there is horizontal motion. There's an inevitable there is inevitable horizontal barbell motion. That barbell motion seems to be, the horizontal motion seems to be less depending on what group of lifters you're in. So A group lifters are better lifters versus B group lifters, which were kind of the lower class lifters in this study. But we still have some horizontal barbell movement, right? So it's not inevitable. So one way that I often think about efficiency in weightlifting or bar mechanics is that it's kind of a way that was presented by Becher and Deutscher in an article in 1999. And they really come to this idea that, you know, the task goal in weightlifting is to move the heaviest bars possible from the floor into this catch position, into that support on the shoulders or into the overhead position. And in order to do that, I need to pull the bar a certain height, right? I need to pull it a certain height so that I have enough time to drop under it and support the barbell. And one way that we often talk about this, or that I think about this, is that I try to lift the barbell to a certain height with a certain velocity. Maybe we can treat the barbell as a quote unquote projectile at that point, right? I've used questions like this for undergraduate biomechanics exams because they're fun projectile motion type of questions and they have some application. And really an interesting question is whether or not the velocity at this point, at this height, actually lets you move the barbell or would produce this travel range that we observe or that we need in order to have the time to drop underneath. And when you actually do the math, you find out very quickly that no, the velocity that you have is not enough, right? So typically the velocity that lifters produce at this point will only produce a quote unquote projectile drift or motion up to a certain height, and they actually have to do some what these authors called rest work on the bar, some active travel. So they have to continue to apply force during this point. So it's not quite as simple as projectile motion. But what is nice is that this relationship, right, this idea pretty much seems to hold across different weight categories. So it seems like it would be something that could be universally applied. And so thinking back in terms of efficiency, the way that Boettcher and Deutsche presented this is that, right, really a way to think about efficiency is that we want to try to maximize the rest work, right? So we want to try to have a high travel of the bar by itself, and only have an optimal Vmax, so a vertical maximal velocity, instead of having an excessive vertical velocity, right? So in other words, to think about this is a very inefficient way is to have very high velocities that would lift the bar very high and then would then crash down on the lifter. And so one way to think about this is that really it should be a ratio, right? That I want to try to minimize the velocity that's needed in order to lift the barbell into that height overhead. So some things that the authors propose is that, right, there should be a minimum velocity that's needed to move the bar into the overhead position in the snatch or to the shoulders in the clean, and that one part of training should really be around trying to establish a critical minimum velocity that you're trying to train towards. Right? Anything above that velocity, right, above that critical velocity would be inefficient, wasted energy, right, wasted effort, however you want to quantify that. And so one way to think about this in very simple biomechanics terms is in terms of kinetic energy, right? So if I have my equation here for kinetic energy, right, a better lifter, right, whatever kinetic energy they could muster up, they would use to lift greater barbell mass. Whereas mediocre or worse lifters are probably favoring the velocity that they're over accelerating the bar, producing higher velocities, or they're not optimizing that vertical velocity. And this kind of also brings me to something that I think about sometimes is a problem with high power outputs, right? Power is pretty ubiquitous in sports biomechanics, and people argue about the definition. How we should use it, if we should use it at all. Certainly for vertical jumping, I think it's falling out of favor. And so in a way, I think that power has probably been an over-focused part of what we do in weightlifting biomechanics, especially barbell power in relation to weightlifting performance for weightlifters. Because it's very easy to artificially increase power outputs by just increasing the velocity rather than lifting heavier weights. So I did some back of the napkin calculations while on quarantine. So since I'm not able to get into my lab. So yeah, one of my favorite lifters from back in the day, Piros Dimas, sorry. So what's cool about him, but there was actually a series of studies that was published, a series of observations by Hiskia in 1997, where he actually collected data on a lot of these parameters that we would need for these sort of efficiency calculations, right? How high does the barbell travel? What's the height of velocity? What's the height of the barbell at its maximum velocity? What's the drop distance, etc. And so if you look at Dimas's performance from the 1994 World Championships, it was 172.5. If I use that data from Hiskia's analysis, I plug it into the equations that Boettcher and Deutsche had, you would actually be able to predict that Dimas would have been able to lift a max of 187.75 kilograms, which indicates a reserve of almost almost 10 kilograms, so almost 20 pounds of weight that he could have been lifting in addition to what he did. And so if we then calculate an efficiency ratio, it brings us to almost 95%. And so it's interesting then, if we look at Demas's overall personal best snatch that came in 1999, he actually reached a performance of 180.5 kilograms. So if we assume that he used very similar kinematics, right, we can plug it into those equations and we will get an efficiency of 99.3%. So again, we go from pretty good to great. And again, this is something that I think of, right, might be a little bit more useful in rephrasing efficiency and performance prediction, monitoring, assessment of Olympic weightlifters going forward. Coming back to kind of velocity and acceleration profiles and looking more at the time series data, we looked at some of this quite a few years ago. Again, we were interested in looking at acceleration profiles in relationship to weightlifting performance, and performance being a measure of somebody's the barbell mass that they lift with respect to their actual body mass. So here we have the acceleration in the black line, the barbell, the acceleration on the barbell during the pull. And in order to kind of look at the profiles or the patternings, we used the principal components analysis, where we try to look at patterns of variation in the barbell and try to correlate that to actual performance. And so one of the patterns that we observed seemed to capture this difference between a very steady acceleration profile, or a very steady acceleration, versus an acceleration that was characterized by a decrease in acceleration, actually negative acceleration during the transition phase, and a increase during the second pull phase. So when we ran the correlation analysis, we found that better lifters, so those who were able to lift heavier weights, followed what we observed with these positive symbols rather than these negative symbols in terms of their acceleration profile. And again, if we do some very simple biomechanical analyses, right, if we have weightlifters that are only able to produce a finite amount of force, a better lifter, right, will lift a heavier mass with a smaller acceleration, whereas a worse lifter or worse technical lifter, right, perhaps lift a smaller mass and use more of that force potential to put into acceleration. An interesting side note, if we try to tie this into kinematic patterns, in this 1999 article, these two authors actually looked at certain movement characteristics that were associated with different acceleration profiles. And one thing that they found is that the acceleration profile that we see in the middle here, where we have a pretty much steady acceleration throughout the lift, is most characterized with a kinematic movement pattern during the first pull, where the torso angle stays fairly constant. So this is often something that you hear weightlifting coaches talk about. Hips and shoulders rise at the same rate during the first pull. And so this kind of gives us an indication of something that coaches talk about, right, from a body posture movement perspective that actually holds over and is related to the acceleration profile. Here we looked at ground reaction force patterns in relationship to, again, weightlifting performance. We did a similar pattern analysis where we used principal components analysis to extract different patterns in ground reaction forces and correlated those to weightlifting performance. And something that we noted is that better lifters, so those that lifted higher weights with respect to their body mass, actually exhibited smaller decreases in the ground reaction forces during the transition phase than worse lifters. The worse lifters, again, here in the negative lines versus the positive lines. And better lifters also had what seemed kind of a temporal shift in the ground reaction force pattern, where we have a quicker transition phase. So this phase from going to the end of the first pull to the beginning of the second pull was done with a shorter percentage as part of the, as as a proportion of their total pull, and with less loss in ground reaction forces during that phase. We've also looked at, I'll try to apply this same type of pattern analysis to joint motion, so joint kinematic data. Here we're looking at hip angle, where positive is our hip flexion angle, or we start in a flex position and then move towards an extension throughout the pull. And again, something that we notice is that our better lifters follow the pattern that's denoted by the positive symbols here, whereas worse lifters follow the pattern that is shown by the negative symbols here. So our better lifters essentially had what we said, a more steady hip angle or torso angle during the first pull, and less of a reflexing of the torso during the transition phase. All right, so that again, that first pull was pretty much done with a very steady increase in torso angle. Change in hip flexion angle is primarily driven by changes in the thigh segment, not the torso segment. And then before we go into final extension towards the end of the pull. With respect to joint kinetics, the one thing that we've noted is that, and if we apply the same analysis, or same pattern analysis to the net joint moment, so here we're looking at knee extension, flexion, extension patterns in the moments. We've noticed that our better lifters seem to follow this positive pattern, or this pattern of positive symbols, where they are producing larger knee extension moments during the second pull. Something that I think is worth talking about briefly is that if we just talk about magnitudes of joint kinetics, because I get a question about this sometimes, that if we look at the kinetics, the knee joint, either knee joint torques, knee joint moments during weightlifting, especially at the knee joint, they don't tend to be that large, right? Here, this is data from Garhammer, 1976. So this is a person, I believe this is a 142 kilogram snatch of one of the middleweight lifters, so almost a 300-pound snatch, where the person is only producing a knee joint moment of about 100 Newton meters, which is not, again, not extremely large. And so it's kind of interesting to consider what else might be driving performance on the kinetic side. So some interesting data that was presented again back in the 80s by Baumann as an analysis of the 1985 World Championships, that we compare data from two lifters during competition. So this is Kristof versus Cinsanis. Both in the super heavyweight category during this competition. Kristof being the world champion, winning the gold medal with a snatch of 202 kilograms, and Cinsanis being in the B group with a snatch of 160 kilograms. We see that Kristof is able to produce, or was able to produce, greater ground reaction forces, right, to lift greater weight. Well, it's interesting that if we look at the knee extension moment during these lifts, we actually see that Kristof produced a much smaller knee extension moment during the final phase than Kristof. Something that Baumann et al. Commented on is that it's perhaps related to the fact that Kristof was able to manipulate the external moment arm in a much more efficient way about the knee joint than Cinsanis. And so there might be some external influence or some other influences of controlling the moment arm, controlling the effective mechanical advantage during the exercise. From that same paper, I also saw that if we look at joint moments across different weight categories and across different lifts, the best correlation that we have, right, between increases in joint moments and body mass or body weight plus barbell weight was actually the hip joint moment and not the knee joint moments. So this has led us to kind of consider of how do we get at some of this with kind of future studies. And this is something that we're considering right now. One of my graduate students is working on this at the moment, where we're looking at net joint moments as well as muscle forces. So we're trying to use musculoskeletal modeling to get at muscle forces during different exercises. So I will just say this is during the squat, so it's not a weightlifting exercise, but we're trying to apply this in the future, hopefully, to weightlifting exercises, where I have my hip extension moment, my knee extension moment. The gray area is the joint moment, and then all these individual lines are the joint moments or the muscle moments created by the individual muscles, the forces they're producing, multiplied by the moment arm of those muscles, and how they're contributing to these joint moments. And so we're doing that for the hip and for the knee. And so we have this for 0% load, and then we have this across different loads. And so something that's kind of interesting to consider, right, is even though we have an increase in joint moment, so that gray area increases, right? So we have hip extension moment increases as we load more weight during the squat. We also have kind of these increases in how much does, for example, the glute max contribute to the hip extension moment, right? That seems to increase. We also have hamstring muscle contribution to the hip extension moment. It's the dashed line here. All right, so that changes. Interesting thing about the hamstrings, right? Hamstrings extend the hip, but they create a knee flexion moment at the knee flexion moment at the knee joint. And so that's what we observed down here. So at the knee joint in the gray area, we have the joint moment that is calculated as a sum of all the individual muscle moments that are produced by the muscles individually. So here, for example, we have the vastus muscles, the joint moment that's created by the muscles, and we see that that's larger than what we have as the net joint moment because we're having to offset the effects of the hamstring muscles. So again, it's just something to consider, that even though the net joint moments might not be that large, the muscle forces might actually be in and of themselves fairly large. And something else that we've thought about a lot, or that we're thinking about a lot, is this idea of absolute versus relative net joint moments, and this idea of strength versus capacity. Is that oftentimes we just focus on absolute joint moments, right? But we don't really know what percentage of your overall capacity this represents. So we're not able to perhaps indicate what are the bottlenecks for performance. Or we often term this, what is the operating capacity of each muscle group during the exercise? So one way that we're kind of looking at this is looking at relative muscle effort, where we're taking the ratio between the net joint moments that we measure dynamically versus the net joint moments from a maximum contraction. So one of the natural things to do for weightlifting is we use the isometric mid-thigh pull, which is kind of shown here. We have a rack where we can position the bar. Weightlifters will do pulls at different positions, and we can kind of get an idea of how much net joint moments are people able to produce during these different positions. And then relating that to the dynamic moments that we measure throughout the motion. One slight problem with that is, or one slight caveat is that, right, we know that the net joint moment depends not only on the joint angle, but also joint angular velocity. So we're trying to use some musculoskeletal modeling. We're using surface regressions, trying to predict what is the maximum joint moment that a person is capable of producing, given the combination of their joint angle, joint angular velocity. And then we're trying to map that out against the dynamic net joint moments that we're actually measuring. So here in the red line, for example, I've calculated the max net joint moment at the knee joint, given these surface regression equations. And then we plot that against the dynamic net joint moment. If we look at the knee joint, right, there's a difference here, so that's good. So Knee joint moment is not reaching its max capacity. At the ankle joint, however, we do see that the green line seems to exceed the predicted capacity at the net joint, or the predicted capacity that the moment that the ankles plantar flexors should be able to produce. So one other issue, right, that comes up a lot when we talk about net joint moments and some of these modeling techniques is the influence of two joint muscles, issues of co-activation, etc. And I'll just say we're trying to get around this by using some more modeling, things such as computed muscle control, where we're, again, predicting individual muscle forces, calculating our net joint moments, right? The actual net joint moment that we observe during an exercise, during a task. But then we also take that same motion, we use some more musculoskeletal modeling where instead of where we're artificially setting the activation of the muscle to 100% essentially. So we're saying, given the motion that we observe, we dial up activation to 100%. We're accounting for the muscle's ability to produce force based on its active length component, passive length, and its force velocity properties. And so we get, again, this net joint moment max that should represent the maximum capacity at the joint. I'm using that then to calculate this relative muscular effort as a ratio between the two. Okay, coming to an end, I wanted to end on the abstract from probably one of the earliest articles on weightlifting that I've been able to find, and probably one of the best titles ever, The Defeat of Gravity in Weightlifting. So here it goes. That weightlifting as the art of defeating gravity may seem a statement of the obvious. It is very rewarding, however, as in all battles, to consider the nature of the adversary. Its relentless nature means that man can only win for a limited time. As we shall see, the earlier he engages the enemy, the more spectacular is his short-term advantage. A long, drawn-out battle is to be avoided at all costs. Man, on the other hand, is apt to injure himself when he tries to mobilize his forces too rapidly. Like the battle commander, the weightlifter is presented with a dilemma, and the information available about his own strength and resources is inadequate to eliminate the possibility of disaster. We must be thankful that at least the foe, gravity, is an entirely predictable one. These words are fairly accurate summary of this paper and hopefully of this presentation. So just wanted to end with thanks to my biomechanics lab group, our strength and conditioning staff, collaborators, many over the years, but especially to Michelle Savick, who gave me a first start in my biomechanics career, ISBS and Vicon for sponsoring this, and Stu for making me give this talk on short-term notice. But I enjoyed putting this material together. So thank you.
Brilliant, thanks, Kristof. Yeah, that was amazing. I think I didn't want to put too much pressure on, but I had high hopes for that, and it was even better than I was expecting. And I love the ending as well, that Grieve abstract. I think I've got a new idol in terms of writing style.
I know, we don't write like that anymore, at least not abstract, so.
Yeah, unfortunately not. But yeah, I think just while we wait for the live chat on YouTube to catch up, if anyone's got any questions, just leave them there. But take a look on the screen at what's coming up over the next couple of months, really. And if you want to keep updated, apparently I'm supposed to tell you to subscribe and click on the little bell thing and you'll get a notification. But yeah, there's a couple of questions already. So apologies in advance for terrible pronunciation as always, but from Supriya Shah, or that's how I'm going to say it and I'm sticking with it, says, so the first one, basically what percentage of 1 rep max should we use for testing the snatch if we want reliable results in a study?
I'm going to go with it depends. I mean, and not to be facetious, but I guess it depends on what what the purpose of the study is. If you're trying to look at maximal competition performance, you probably need to use loads, right, that are close to 100% of maximum. weightlifting research is difficult because you can't ask people to do too many lifts at 90%, right? We can't just say, here's a mean of 10 repetitions that somebody did at 90 to 95%. So in a way, I think it's the nature of the beast that you're stuck with, right? Few repetitions. If Priya has more questions, feel free to email me. I would be happy to chat about this more. Right. But again, it's in competition, you only have 3 attempts, right? And those attempts are typically at either different loads or you have a failed attempt in there. And so it makes it really difficult to talk about this issue of reliability, which maybe we conveniently ignore. So.
Yeah, I think the question, looking again and doing my job properly, was specifically around studying lift trajectory, which I guess is still it depends, and even the trajectory might depend on the actual load as well.
Yeah, and I think it's interesting because I didn't have that slide in there because I feel like I went over time, but we're starting to look at trajectories a little bit in the variability in trajectory that we observe from trial to trial, and we're trying to parse that out between meaningful variability versus just noise. And so it's an interesting subject because I think it gets at the idea of what variability, is there variability in the barbell trajectory, and does that actually matter to some extent, right? What do coaches try to fix? If there's variability that's not related to the performance outcome, then let that variability run wild, I say. So
yeah, I think alludes to the whole functional variability debate as well. Yeah, and the second question is around the horizontal displacements. I know early on in the talk you had the kind of vertical reference lines, and then saying an early view of efficiency was essentially any horizontal movement or force was inefficient. But the question is, do you think there should be a specific recommended range that's maybe acceptable or unacceptable, or should it be as close to vertical as possible? Or how would you, I guess, give some recommendations around that?
Yeah, so I mean, in some of the original, again, I had another slide. In some of the original papers, I think Garhammer has a range, right? So there's a range for backward displacement during the first pull should be between 3 to 5 centimeters, maybe, right? Forward displacement should be between, right? So there are ranges. And of course, right, it's probably not a linear relationship either. Right? There's probably a nonlinear or a curvilinear relationship where you need some horizontal movement to properly do the lift, right? To be able to turn the barbell over to produce that horizontal acceleration to counter, to actually turn the barbell over. Do you want the bar going all over the place in the horizontal direction? Obviously, no. So I think short answer, yes, there are ranges. And maybe we should look at those with not with a linear lens, but maybe a curvilinear type of analysis rather than linear regressions.
Brilliant. Yeah, I think I've got a couple of questions I could ask. Well, potentially save those for another time. I think if anyone wants to find out more about any of your research or just any of the ideas you've got, is there a best way of either getting in touch or checking that out?
Yeah, either Twitter or email. I'd say most of my research articles are on ResearchGate, and if somebody can find it quickly and they send me an email, I'd be happy to share the stuff that we have. So
brilliant. And the link to Kristof's ResearchGate page it should be below the video in the description as well. So that should have, and I know when I looked earlier, quite a lot of them were open access as well. So you should be able to access those on there. So yes, brilliant. Thanks ever so much again, Kristof. And thanks everyone for listening, and hopefully see you again next week.